All right, ladies and gentlemen, this class recording has started. So, last week on Wednesday, we started in on section 4.4 dealing with projectile motion. And projectile motion is analyzing the motion of an object as it moves in 2 dimensions. And regardless of the fact that Luke doesn't like it, the one big thing that we discussed was the idea that the horizontal and the vertical motions are independent of one another. Even though there are 2 things going on at once, a horizontal motion and a vertical motion, the fact that one is occurring doesn't affect what's going on with the other one. And we talked about the idea that, if I have the ball, right, and I throw it up in the air, we talked about in chapter 3, right, it slows down on the way up, it stops, it speeds up on the way down. And because the same gravitational acceleration is acting on it the whole time, the up trip takes just as long as the down trip, right? How fast it's going here is equal to how fast it's going when I catch it, blah, 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 right? But that doesn't change if I add a horizontal motion to it as well. So if it takes, 0.6 seconds to go up, it will take 0.6 seconds to come back down, whether I'm standing still like this, or whether I walk and I throw it up like this, as long as I throw it up with just the same speed as it had when I was standing still. Okay? And we talked about we did this video, right? Not that I'll play it again for you, but the video of the guy standing on the ladder, right? And he dropped the bocce ball and he threw the bocce ball, right? The time it took for the objects to reach the ground didn't change, even though one was moving both horizontally and vertically, as opposed to just moving vertically. Okay? All right. However, getting into this section a little bit more, it still deals with motion. And just like when we were in chapter 2 and chapter 3, we're still looking to describe motion. We're still dealing with kinematics. It's just now we have more things to take care of. Although the terms and the concepts don't change. There's just more of them. So, at the bottom, where is it? Oh, sorry. On Thursday, maybe we didn't talk about this on Thursday. Our discussion of motion in this section is going to be limited to what we refer to as projectile motion. And if we pop up the definition of projectile motion here, it says, and you guys have this in your packet as well, it says an object that is thrown, kicked, batted, or otherwise launched into motion and allowed to follow a path determined solely by the influence of gravity. That part at the end, determined solely by the influence of gravity, is the important part for this section. Another cool feature of this that I learned yesterday, in case this wasn't good for you and you needed, Elise, Simran, if you need a little bit, I can change that into Espanol if you need to. So, if you feel like, so, patiado, opuesto, so, yeah, gravidad. So, I'm just saying that's, so if you need it, I can turn it into Spanish for you, so, Say again? We'll just do all of our definitions in Spanish on Fiesta Friday. So, all right, good there. Okay. I mean, with the definition of a projectile, not Fiesta Friday, because I know you don't have any problem with Fiesta Friday. So, it is talking other than the fact that it's not currently Fiesta Friday. That's the only problem with Fiesta Friday. So, all right, the biggest thing there. These 2 bullet points that show up on the bottom of your packet, right? Air resistance can be ignored, and the acceleration due to gravity is constant and directed downward with a magnitude equal to 9.81 meters per second squared. Those are going to be the 2 important factors in analyzing this projectile motion. And in doing that, let's take a look at, you guys, it's the top of the 2nd page of your packet. that's called motion equations for projectiles. Like I said before, we're still dealing with motion, and therefore we want to describe the motion, right? Where is it? What is it doing? What's it going to do next? When are all these things happening? And at the top of that second page there, right, motion equations for projectiles, we have an equation that hopefully looks familiar from back in chapter 3, okay? This is the equation that relates the position of an accelerating object to its initial velocity and then the time that it's accelerating, okay? We used this back in chapter 3 when we talked about accelerated motion to figure out where things are, etc., etc., etc. Now, that equation still applies. It still relates position with velocity and acceleration and time. All of those things are still true. But when we're dealing with projectile motion, we need to analyze both aspects of the motion separately. So, here, all we've done is taken that equation up at the top and applied one of them to the x-axis and one of them to the y-axis, because we have to separate them. We have to analyze them separately. So we just added x and y subscripts to the different factors in that equation. We changed our positions from x final and x initial to y final and y initial, because we're dealing with the y-axis now instead of the x-axis. But when we look at that a little bit more closely, right, we can make this equation a little more specific to the projectile motion itself. First, we said that the only thing that's going to affect the path of the projectile is gravity. Meaning, gravity acts on our vertical axis, on the y-axis. If we neglect air resistance, which we will in doing problems in this section, there is nothing horizontally to change the motion of the object. Even though it may be moving horizontally, gravity is still acting on it vertically. If there's nothing to change the motion, there is no acceleration. Is that good? Right? If there's nothing there to make it go faster or slower, like air resistance, the horizontal acceleration becomes 0. And then this equation turns into this equation, where we just drop the whole last term, because if the acceleration is 0, we don't have to worry about it when analyzing that portion of the motion. Okay? Good there. For the y equation, for the vertical equation, we only have to, well, we do have to worry about acceleration because gravity is accelerating that object. But we know that the acceleration of gravity here on Earth is a specific value, and we assign that value the letter g. So here, we transform this equation, and we substitute in g for acceleration, right? But we know here on Earth that that has a specific value, that value being, let's not go negative 9.81, right? The acceleration is just 9.81, right? The negative starts implying what? Direction. Therefore, I want you to change something in these equations right here. Okay? These are all addition signs. But here, they sort of take the liberty of saying, well, gravity always acts down, so we're just going to call this negative. All right? You can't do that. The equation isn't a minus sign. The equation is a positive sign. If gravity is in the downward direction and we call down negative, it becomes negative, but you can't just change the equation like that. Okay? So here, let's make this a plus sign in the actual equation. Okay? Good there. like it says, right, like the heading on this little section says, these equations show us the position of an object in the horizontal direction and the vertical direction as time passes as this object moves in 2 dimensions. Okay? Good there. All right. Let's take a look at active example 4.9, dropping or determining the position of a dropped ball. So here, and there we are. All right, so it says, a person skateboarding with a constant speed of 1.30 meters per second releases a ball from a height of 1.25 meters above the ground, as in figure 4.25. Given that x initial is 0 and y initial is 1.25 meters, find xf and yf for the times t equals 0.250 seconds and t equals 0.50 seconds. Okay? All right. I'm going to take you through the process of doing this. All right? Most of you probably could find the numbers that you need to in this problem and plug them into the equation, because this is the first example in section 4.4, so they want to make it as straightforward as possible. But I'm going to take you through a process that I think will help you even when the problems maybe get a little bit more complex. Okay? So, here's what I would suggest to you. In starting problems in projectile motion, dealing with 2 dimensions, I like to make a table. And that table has 3 columns. Regardless of what order you put them in, we'll label one column X, representing the horizontal motion, the horizontal portion of this motion, and then we'll label one column Y, where we keep track of the vertical portion of this motion. Now, I kind of made mention already, at least once today, even though it's 2-dimensional, it's still motion, and we're still describing that motion. So far, in chapters 2 and 3, we've introduced 6 things that we would like to know about a motion. And if we know all 6 of these things, we do a good job of accurately describing the motion. All right? Do we want to list them, or do you want me just to tell you them? You know what? I'll just tell you so we can go through it a little bit faster. Okay? All right. First, we want to know where an object starts. In this case, though, we have to worry about 2 wheres, right? We have to worry about where it starts on the x-axis, but we also have to worry about where it starts on the y-axis. Second, we want to know where something ends up, right? Where does it ultimately end up? What is its final position? But again, we have to worry about where does it end up on the x-axis, but also where does it end up on the y-axis. Next, what was its initial velocity? What was it doing initially at the beginning of this motion that we're trying to describe? What was it ultimately doing at the end of this motion that we're trying to describe? Did it change throughout the motion? And then finally, how long did this motion last? Yeah, it is a lot of stuff. Although we'll see that filling this table in sometimes isn't as complicated as it seems to be. All right. This table is the key to getting us from where are we now to where do we want to be. But we've talked about that the first thing we should do when solving problems is what? Where should we go first before we see what we have? What we don't have? What are we trying to find, right? So in this case, right, this is pretty straightforward, right? Find xf and yf. right? Because it's the first example here, right? So we know that this is going to be a question mark, and that's going to be a question mark. All right. Next, and I will start off the problem like this. Next, there are two things in this table that we can fill in right away before we even read the problem. There are two things that are going to be the same in every single problem that we do going forward in section 4.4. All right? Here. The only thing that's affecting the motion of the object is what? Gravity. Gravity causes an acceleration, right, Brett? What's the acceleration of gravity? 9.81. However, in this problem, which way does gravity act? Which axis are we talking about? Y-axis, right? We're talking about the vertical. So acceleration on the vertical axis is going to be 9.81. Hold on to that thought just for a second, okay? We know that the acceleration on the vertical axis will be 9.81. If gravity is the only thing affecting the motion of this object, which we're going to assume, we talked about that, is there anything affecting the motion of the object on the horizontal axis? So what, if there's nothing affecting the motion, what does the acceleration have to be? 0. Those two things are going to be the same in every problem that we do in section 4.4. If we included air resistance, that would change, especially the horizontal, but it would change the vertical as well a little bit. But we're not going to include air resistance in our analysis of these problems. So these two are going to be the same. Okay? All right, good there. Luke, let's address your concern. Okay? This is acceleration. It's a vector quantity. It needs direction. But before we can determine the direction of things, we have to do what? Reference point, coordinate system, all those fun things, right? In this problem, they have done that for you. I'm going to draw it in, but here, right, labeling this point right here, O, that's going to be our origin, right? Meaning that's the intersection of, meaning that's the intersection of our y-axis and our x-axis. I drew them a little bit off of the lines in the picture just so we can see them, right? If this is the intersection of our x-axis and our y-axis, we can kind of go with the convention that we've developed through math class. Positive on the x-axis is this way, negative on the x-axis is this way. I'm not sure why this is drawing right now, but okay. And then positive y is up and negative y is down. Okay? Luke, taking that into consideration, which direction is our acceleration going? Negative. All right. So we can make that negative 9.81. Now, let's go up in here and start pulling out some information. Other things that we can get that will help us as we fill in this chart. Because this chart is going to determine how we're going to get to the final answer that we're looking for. So there's a couple of things that they made totally obvious for us, right? X initial is 0. Y initial is 1.25. If we take that spot right there as being the starting point of the basketball, as it is in the picture, right? If we think about it in terms of an ordered pair that's describing the position on an XY axis, right? That would be the ordered pair that describes the position of that basketball at the beginning, right? Therefore, that's our initial position on the x-axis. That's our initial position on the y-axis. That goes there. Okay? All right, next. This one gets a little bit trickier, all right? It says, person skateboarding with a constant speed of 1.30 meters per second. That's how fast the person is moving. But if the person is carrying the ball, and the person is moving at 1.30 meters per second, guess how fast the ball is moving? 1.30 meters per second. Now, that's where this problem, that's where it becomes a little bit important for this problem though. He's carrying the basketball. Meaning that this basketball is moving which way? It's moving horizontally, right? Because he's just holding it as he carries it, okay? At the moment that he lets the ball go, the instant that he lets the ball go, that ball is traveling horizontally. It's not doing anything vertically, okay? Now, immediately after he lets it go, what starts happening to it? It's, right, it's going to start moving which way? Because gravity's going to pull it down, right? Will it lose that horizontal motion, though? Let's go this. Okay, sorry. We'll do this part, right? So, the instant that the ball is let go, right? It's moving 1.30 meters per second horizontally, but it's not doing anything vertically. Just like in chapter 3, right? If we take this ball and we drop it, the instant that I let it go, what is it doing? At the very moment I let the ball go, is it doing anything? No. So its initial velocity is 0. Now, immediately after I let it go, it starts accelerating, its speed changes, right? And that's going to be the case here as well. But at that instant that the basketball is let go, it is only traveling horizontally. Now, right after it's let go, like we said, gravity starts acting on it and starts affecting it on which axis? Y-axis. On the y-axis, what will start happening to that basketball? What happens to that ball when I drop it on the y-axis? It accelerates. Specifically, it starts going faster. And that will happen here too. But it will continue to move horizontally because there's nothing to stop that horizontal motion. And as a result, it will take this curved path to that point right there. If we assume that to be 0.250 seconds after it's dropped. Right, go ahead. Yep. They are, this is, like in the picture, right, this is just showing us positions, right? So in this case, right, when the basketball is there, that would be these 2 points right here. We're trying to find out what are these values. That would be the ordered pair that would represent the position of that basketball after a certain amount of time. It has nothing to do with where the object is, but it does have to do with the other factors that affect where that object will be. Because all these things will ultimately determine where the object ends up after a certain amount of time, but they don't necessarily show up on this picture. Okay? All right, one more thing that we know for sure about part A, and I underlined it in purple, right? What did I underline? The time. Now, something to keep in mind. Even though you don't like it, Luke, right? Horizontal and vertical do not affect each other. Okay? However, they do occur simultaneously. It's moving horizontally and vertically at the same time. Meaning, if I know, yikes, Meaning, if I know how much time it was traveling horizontally, guess what else I know? How much time it was traveling vertically. On that table, on this table that we use to analyze these projectile motion problems, right? The time always has to be the same horizontal and vertical. Always. It's the only row on the table where the numbers have to be the same horizontal and vertical. We'll encounter some problems a little bit later on where we might see one row where the number is the same horizontal and vertical, but time always has to be the same. Okay? Luke, go ahead. Give me 2 days and I'll show you. Okay? The one that might show up is the initial velocities might be the same, right? Krista, go ahead. So that's all right. Like, yeah, like that ordered pair, right? That's going to represent the initial positions of that object on the x-axis and the y-axis.
Why wouldn't the acceleration be positive? Because it's what the origin is at.
Now, in this case, Krista, they chose to make the origin in a different place from where the basketball actually starts.
So it didn't specify the origin.
Right.
Okay. So
Now,
this is a different thing.
well, the thing though, that would change these two numbers, but it wouldn't change any of these numbers. Okay? Remember that the sign, especially on acceleration, is the direction, but not necessarily where. Even though on the y-axis, this basketball is above 0, it's on the positive side of 0 on the y-axis, gravity is still pulling it in the downward direction. And downward on this axis, on the y-axis, generally is negative. Does that make sense? Yep. No, because it didn't start at 0, right? So it's starting at, right, the final position, actually that's the next problem, so, you know, but yeah, that's more, these are more where it starts, right? But that doesn't affect necessarily the direction on the acceleration or the velocity, because those have to do with which way we're going, not necessarily where we are in relation to the x-axis. All right, good there? Right, good. Depending on where we set the x-axis, sure, right? In this case, it's not going to be able to because we've put the x-axis on the ground, okay? But if we chose to make the origin there, right, then all of our y positions would be negative because they're below 0 on the y-axis. Does that make sense? That's more of a function of where do we decide to put the x-axis and the y-axis, which can change depending on the problem that we're doing. No, because regardless of whether we put the x-axis here and make the origin where the basketball stops, or whether we put it here, gravity is still acting in the same direction, right? It's still going down, which is still negative on the y-axis. So that won't change the sign on that. All right, good there? Okay. Now, it's a matter of using these equations to get what we need to know, right? One thing I just want to remind you of, right? Here, I changed that to a positive sign in the equation itself. But in this problem specifically, acceleration is negative, so we're plugging a negative number into that spot right there, right? So go ahead, plug in the numbers that you know, right? Solve for what you need to solve for. Keeping in mind that some of these things go away depending on the specific values in this problem, right? Like, this is going to go away, and this is going to go away. So go ahead, plug in the numbers there. Let's solve for what it asked us to solve for. Again. Oh, sorry, it's already not there. This is what? Yes. Say again. G is our acceleration of gravity, right? All right. Good with those two? Just correct, going back to the discussion we've had, right? The fact that y final came out to be a positive number, right? Meaning that it's still above the x-axis, right? That's just where, but it's lower than where it started on the x-axis, meaning it went in the downward direction. Okay? Good there. All right. Okay. One thing I want to do here, let's finish up this next problem. And then I think we might call it a day because we're getting pretty close to the end here, right?
Let's talk about black holes.
Yes, please. 0.325? Is that what, did you get that, or were you just waiting for me to tell you so you didn't plug it into your calculator? It's okay, at least. It's okay. All right. So here, right? Question number 36, which shows up at the bottom of your page. How much time does it take for the ball to land? So let me slide this over here so we have a little bit more room. Now, we could go through the process. You guys still have all of these things written down. Let me do this again. But, say again? True, right? Yeah, there's some things that are going to change and some things that won't change, right? Actually, yeah, let me do this. Let's see if this works. Nope, not that one. Let's go here. I suppose I could. No, I don't have the problem. So. Yeah, it is, but that's just. There's going to be one thing though that I'm not going to like about this. Okay, so we have to change a couple of things about this though, right? First, what is this question asking us to solve for? It's asking us to solve for time, right? So these are no longer, these are no longer 0.25, right? They're question marks. Although we just learned, right, that as long as we solve for time on one side, we can automatically get it for the other side. It doesn't matter which one we have, because they have to be the same. Okay? Here, initial positions don't change, but Caitlin, you kind of mentioned this before, right? What is our final position going to have to be in this problem? What's y final going to have to be? 0, because going back to this picture, right, when it gets to the ground, even though it's not in the right spot anymore, when it gets to the ground, that's 0 on the y-axis, right, because that's where our x-axis is. So here, right, y final is no longer an unknown, it's actually 0. None of the rest of the things change though. Okay? So we had two equations, right? Okay? You might be tempted to use the red equation because this blue equation has t in two different places, and that seems like a big mess, okay? But do we have enough information to solve for t in the top equation? We don't know what x final is, so we can't use that equation. But because v initial on the y-axis is 0, that term goes away. Okay? And we can start plugging some things in, right? We said that this is 0, this is 1.25 plus 1/2 negative 9.81 times t squared. Okay? Mathematically, to get t, what mathematical operation are we eventually going to have to do? We're going to have to take the square root, meaning we have to take the square root of a positive number, yes? Okay? When we take 1.25 over to the other side, what are we going to do? Well, technically you're subtracting it from both sides, right? So you'll end up with negative 1.25 equals negative 4.905 t squared, which is all good, because then we divide negative by negative. When we get a positive number, we take the square roots. Did you finish this? Yeah. What did you get for the time?
The time is 4.505.
Which we should probably go to
505 seconds.
505 seconds. Come on. There we go. Say again? If you take 1/2 of 9.81, right, because that's this term right here, right? So 1/2 of 9.81 is 4.905. Because you got to do that first, right? Because here we're multiplying all three of these things together, right? So we can multiply 1/2 times 9.81 first, then divide by that answer. Hey, there's a couple of problems on the homework for this evening. Answers are posted, similar to what we did in class, although we didn't get all the way through. I know that's shocking that we didn't get all the way through what I wanted to get through, but it's a good discussion for the first day. So, you know. Yes, Luke.